Hello, hi. Welcome to EDUHUNT IIT and NEET Foundation classes. This is Sukumar. See, in the previous class, we completed the topic called hybridization. We all know how to determine hybridization, what is hybridization, how to determine hybridization, and what is the purpose of hybridization. We completed that. And among those, one thing about hybridization which is important is, with the help of hybridization of the central atom, we can predict the geometry or shape also, right? For suppose, if you take the molecule methane, the central atom hybridization, we know it is sp3. sp3 hybridization suggests tetrahedral. Okay, fine. And tetrahedral bond angle, ideal bond angle is expected to be 109 degrees 28 minutes, and molecule seems to be like this. Okay, tetrahedral geometry. So it means if you know the hybridization of the central atom, we can predict the geometry. It seems to be like that, right? We can predict the geometry, we can predict the shape, we can predict the bond angle. It seems to be right here. Yes, of course it is correct. But for suppose, I'll explain one more example. See, boron trifluoride. Immediately, what is the hybridization of the central atom? The hybridization of the central atom is found to be sp2. And this hybridization suggests the geometry to be the why? I told you during in that hybridization class. After the formation of hybrid orbitals, the hybrid orbitals will orient in space. They arrange in space in such a way to have minimum repulsions. And if there is 3 hybrid orbitals, sp2 hybridization gives 3 hybrid orbitals. If there is 3 hybrid orbitals, the arrangement which gives minimum repulsions will be trigonal planar, right? Okay, fine. So it means boron will be the central atom and the trigonal planar geometry will be like this: fluorine. To understand the shape or geometry, I am making dotted lines. Are you getting this, right? It seems to be very clear that if you know the hybridization of the central atom, we can predict the geometry, shape and bond angles. Bond angle, the ideal bond angle of trigonal planar will be 120 degrees. That was true only. But the point is, knowing the hybridization of the central atom is always not sufficient to predict the geometry or the shape or bond angles of every molecule, every ion, right? There are some deviations, right? For suppose, in the same like methane, if you take NH3 molecule and you determine the hybridization of the central atom, it comes out to be sp3 like this only. So that geometry has to be tetrahedral. Bond angle has to be 109. But in the case of ammonia, the bond angle is found to be 107 degrees. And if you take H2O molecule, the hybridization of the central atom is again sp3 like this. And the suggested geometry, sp3 hybridization suggests a tetrahedral, and bond angle expected to be 109, but the practically observed bond angle is 104 degrees here. So always the hybridization of the central atom is not sufficient to explain the geometries or shapes or bond angles of every molecule. Okay? Yes. So we need separate theory to explain the geometries or shapes or bond angles of any chemical species, whether it is a molecule or ion, right? And that was valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Let me write the full name. Valence shell, valence shell, electron pair, repulsion theory. See, the name itself suggesting, or the name itself telling lot of things, or this name is giving some idea about the theory, right? Because see, valence shell, that means there is a valence shell of the central atom. There is electron pairs in the valence shell, and anyway that electron pairs are going to decide the geometry, like that, right? Yes. In the beginning, this theory was, originally this theory was proposed by Sidgwick and Powell. Proposed by Sidgwick and Powell. Sidgwick and Powell. This theory was proposed by Sidgwick and Powell, but again there are some exceptions. So it was later developed by Nyholm and Gillespie. Not Nyholm, Nyholm and Gillespie. Excuse me if there is any spelling mistake, I don't bother generally spellings. And Gillespie. So the point is, these two scientists, the first two scientists, Sidgwick and Powell, these two scientists proposed this theory in the beginning. After few years, that means around 1940, I think, these two scientists proposed this theory. After around 1957, those years, these two scientists developed the same theory to apply the concept to every molecule and every ion. So simply what? So we are going to first discuss what Sidgwick and Powell proposed, and what are the points added by Nyholm and Gillespie to make the theory better. Okay? Yes. First of all, according to Sidgwick and Powell, generally every molecule has central atom, right? Molecule has central atom. I am taking molecule, you can take ion also, right? Molecule has central atom. Okay, fine. And that central atom has valence shell, that means outermost shell. For suppose, if you take methane, carbon is the central atom. If you take ammonia, nitrogen is the central atom. If you take PCl5, phosphorus will be the central atom. Like that molecule has, or ion, you can take ion. If you take NH4 plus, nitrogen is the central atom. If you take ClO3 minus, chlorine will be the central atom. Like that, every molecule or ion has a central atom. Central atom has valence shell. Next, valence shell consists of electron pairs. Valence shell consists of electron pairs. Yes, valence shell consists of electron pairs, right? How? For suppose if you take methane molecule, see, this is the central atom. Now the valence shell means this entire portion. This entire portion is the valence shell. That means you can take this valence shell of carbon has a 1, 2. They bond pair, 4 bond pairs. So 4 pairs, right? Yes. Similarly, you can have lone pairs also. But the point is, valence shell consists of electron pairs, and though the repulsions between the electron pairs will determine the geometry. Or shape, you can do. So simple. In the beginning, the original theory was so simple. Molecule or ion has a central atom. Central atom has a valence shell. Valence shell consists of electron pairs, and the repulsions between the electron pairs will determine the geometry. That's it. And we generally theoretically can't predict which geometry is suggested for which type of electron pair. See, the point is, why the electron pairs are determining the geometry? Because around this central atom there is 4 bond pairs. Obviously there is repulsion. More repulsions means more energy. More energy means less stability. So these 4 pairs has to arrange in space in such a way to have minimum repulsions. And Sidgwick and Powell suggesting that if there is 4 pairs, the geometry which gives minimum repulsion is tetrahedral. Like that. According to Sidgwick and Powell, for suppose you take, if there is 2 pairs, around the central atom, like if this is the central atom and there is 2 pairs. So when there is 2 pairs, the geometry which gives minimum repulsions is linear. And when there is 3 pairs, the geometry which gives minimum repulsions is trigonal planar. Okay, like this. If you know the number of electron pairs around the central atom, with that electron pairs you can predict the geometry. That's what given by Sidgwick and Powell. Okay, and that was later developed by Nyholm and Gillespie. I'll tell you later. See, if there is 4 pairs, in the valence shell of central atom, when there is 4 pairs, the pairs can be lone pairs and bond pairs. That's different thing. The 4 pairs. If there is 4 pairs around the central atom, the geometry which gives minimum repulsions is tetrahedral. So that means central atom, one pair, second pair, third pair, fourth pair. So this is a trigonal planar geometry. This is the tetrahedral geometry. If there is 5 pairs, the geometry which gives minimum repulsions according to Sidgwick and Powell is trigonal bipyramidal. That means you have to make a trigonal part with 3 pairs, 3 electron pairs. This is the trigonal portion. Let me make this is the trigonal portion, and above the plane, below the plane, I am making 2 pairs, right, like this. So trigonal bipyramidal. So when there is 5 pairs, 5 electron pairs around the central atom, the geometry which gives a minimum repulsions is trigonal bipyramidal. Trigonal bipyramidal. Okay, like this. So if you know this number, you can simply predict the geometry, right? Yes. Next, 6 pairs, then it is going to be octahedral. Central atom, 4 pairs in square planar manner, square planar. Make a square planar geometry like this first. Square planar geometry like this. Now make 2 more pairs, 1 pair above the plane, 1 pair below the plane, like this. So this geometry is octahedral. This is called octahedral geometry. Octahedral geometry. Okay? Yes. Similarly, when there is 7 pairs, then you are going to have pentagonal bipyramidal. Pentagonal, that means if it is the central atom, make a pentagon with 5 pairs. See this square plan, actually it is looking like this on the board to you. Actually it is like this. Now 1 pair above, 1 pair below. Okay. Similarly, this pentagonal portion also like this looking to you on the board. But actually it is like this. Now make 1 pair above, 1 pair above, 1 pair below. So it will be pentagonal bipyramidal. Okay, yes. But the point is, only these points, like if the molecule have a, only these points, like a molecule has a central atom has valence shell consists of electron pairs, and the electron pairs repulsion will decide the geometry. How? When there is 2 pairs, to have minimum repulsions, it will be linear. 3 pairs, trigonal planar. 4 pairs, tetrahedral. 5 pairs, trigonal bipyramidal. 6 pairs, octahedral. 7 pairs, pentagonal bipyramidal. Okay, it's fine. It's very good. But the point is, there is the difference between having lone pair and bond pair. For suppose, if there is 6 pairs, Sidgwick and Powell talking about 6 pairs. When there is 6 pairs, the suggested geometry is octahedral. But the point is, the question is, all these 6 pairs are bond pairs or not? If any of among these 6 pairs, if there is a 1 lone pair and 5 bond pairs, when there is 2 lone pairs and 4 bond pairs, for suppose if these 2 are lone pairs and these 4 are bond pairs, that's different case. When there is 2 bond pairs, rest of the 4 are lone pairs, that's different. So having lone pairs and bond pairs will make some changes to this concept, and that's what did by Neom and Gillespie. So what Neom and Gillespie added to the theory of Sidgwick and Powell is lone pair occupies more space on central atom compared to bond pairs. So this is the point added by Neom and Gillespie to the theory already proposed by Sidgwick and Powell. What they did? Lone pair occupies more space on central atom compared to bond pair. So what happens with this point? With this point, a lone pair repulsion is more than lone pair bond pair repulsion, and that is more than bond pair repulsion. See, a lone pair repulsion is going to be more than lone pair bond pair repulsion, and that is going to be more than bond pair repulsion. Okay, so this point will make some changes in the ideal geometry or the bond angles we expect from the Sidgwick and Powell concept. Okay, yes, and similarly, when there is a multiple bond, triple bond causes more repulsion than double bond. Obviously, double bond causes more repulsion than single bond. So this is a repulsion. This is order for repulsion. But the point is, while determining the geometry or the shape from with the help of this valence shell electron pair repulsion theory, please consider double bond or triple bond or triple bond, both the multiple bonds. These two multiple bonds has to be considered as one bond pair. See, in triple bond there is 3 bond pairs, but while the process of determining the geometry from Vesper theory, please consider triple bond as a single bond and double bond as a single bond. Single bond already a single bond. Okay, let me explain this concept.